propagation. Let's see. All right, we were talking about power flow last, is that right? Anything else?
That's what we were about to start.
About to start, yeah, all right, where we left off. So now what we're gonna do, we've described waves mathematically, both forward traveling and reverse traveling waves, both E and H, in complex medium. And we found out, there are a few things that are gonna be important. One is the complex, or the intrinsic impedance, and that's always gonna be the square root of J omega mu over sigma plus J omega epsilon. The propagation constant is alpha plus J beta, and that's equal to the square root of J omega mu times sigma plus J omega epsilon. All right, those are two very important concepts. If it's lossless, it's only J beta. So now, when we got into the general forms for propagation, the E field in a given region, let's do this in the phasor domain with some constant E naught, and it's times E to the minus gamma Z plus the reflection coefficient. Did we talk about reflection coefficient class or not?
I don't think we.
No? Okay. I'll stop there. What we did not talk about reflection coefficient, is that right? All right, thank you. That's what I needed to know. So in general, though, we talked about an equation where we had the E field as a function of Z being equal to some E0 plus E to the minus gamma Z, this would be in the region, plus E0 minus E to the plus gamma Z. That I'm sure we talked about, correct? And this is going to be in a certain direction. We'll call this oriented AX, and it's traveling in Z. Now it would give rise to an H field, an H of Z, that would have the components H naught 0 plus E to the minus gamma Z plus, and that's the minus there, plus H naught minus E to the plus gamma Z, and that would be in the Y direction. Do y'all remember this class? We did write these down, correct? Forward and reverse traveling waves. So now, I'm going to first cover power before I cover reflection. Let's assume for now, break it right there, we'll come back to these. Now we're going to talk about power flow and the definitions. In general, if you're talking about an electric field, whether it's propagating in the forward or reverse direction, this is propagating waves. What you can say is the power that's associated with that is P av, and it's a function of Z. It's also usually defined in terms of a complex, in terms of what's called a pointing vector. This is the more common definition, and that's S av of Z, and this is called a pointing vector. Both are the same, and it's equal to 1/2 the real part of E cross H conjugated, and this is going to be for the phasor domain, the phasor form of E and H. Now we did this last time. Do y'all recall that? I put that down. I don't know if we finished this or not, but I'm going to finish it right now. So when I have the E field, I'm only going to do this for a positive Z traveling wave. So when I talk about that, the E field for a positive traveling wave is given as some scalar constant E naught, E to the minus alpha Z times E to the minus J beta Z. I'm going to leave it in the AX direction, and this is a plane wave that's traveling in the Z direction but decaying exponentially, possibly. Now, how do I get the H field? Remember, this is the phasor domain. H field can be gotten by just taking 1 over the actual characteristic impedance of that media times AP, which is a unit vector in the direction of propagation, and it's crossed into the E field. I gave you that one last time. Do you remember that class? We're in the phasor domain still. So for this, the H field would be equal to really, by the way, what is the direction of propagation for this wave?
Z direction.
positive z direction, so you can just say that a propagation, the unit vector in the direction of propagation is simply az. So this is going to be 1 over the impedance, right? And it's going to be times az crossed into the E field. Well, the E field has got E naught, right? And it's got e to the minus gamma z, and it's e to the minus j beta z in the ax direction. That's an x. Do y'all agree with me, class? Now, when we cross z into x, what do you get?
Minus y.
Think about it. This is the way you do this. You go x, y, z, and back all positive. If we go z, y, x, all negative. So if we go z cross x, that's the next one, it's a positive ay. And you can get it using the right hand rule. I don't know if who showed you this, but if you just take your right hand, assuming you have one, you take your thumb and put it in terms of the first vector when you're crossing it. And this one, it's z, right? So let's say that z is vertical. Doesn't matter, right? Z, and then you use your wiper arm, that's your index finger, it's called a wiper arm, and you cross it into the next vector, x. So let me just do it this way. How about I do it this way? We'll call this x, call this y, call this z, all right? This x is out of the board. So if I look at a z crossed into ax, take the wiper arm, cross it in over the smallest angle, which is 90 degrees, not the back angle, which is going to be 270, but the smallest angle, crosses in the x, thumb points in the direction of propagation, right? Or into the result, which is y, in this case. You with me? So that's ay. And that means this is going to be equal to 1 over eta, and it's going to be E naught, right here, e to the minus alpha z, e to the minus j beta z, and then it's in the ay direction. I'm going to make one other comment right here. It's important to listen to me. Now, eta has a magnitude and an angle. Do you all hear me? Eta is this. It can be just strict real if it's basically lossless. Like it's about 120 pi ohms or 377 ohms here in the atmosphere. But it can be lossy too, so you got to be careful. In metal, remember we said metal had an intrinsic impedance that was very small and it had an angle of 45 degrees. Do y'all remember that? Here, the way I like to write this is 1 over the magnitude of eta, whatever it is, and then it would normally be at e to the j, the angle of eta, right? Well, if I take 1 over e to the j, I get e to the minus j, don't I? So I put the angle up top, and I put it as e to the minus j, and this just the angle associated with the intrinsic impedance. And now I'm going to do one more thing, if you listen. I'm going to add e to the minus j beta z and the angle into one argument, all right? That way it compacts it. So if I do that, I can say this is equal to E naught over the magnitude of eta. It's times e to the minus alpha z. These are all real things. These are strict real. Then I put down e to the minus j quantity beta z plus the phase angle, theta n. I don't have to do it that way. Maybe I shouldn't, but I'm going to. Times ay. And that's the H field. That's the H field by definition. Either one of those. Are you with me? Now we're going to go get the power. This is the power. This is an important one. This is the power for a wave going in the positive z direction. So the average power as a function of z is 1/2 the real part of the E field. That's the E field here. So it's going to be E naught, right, times e to the minus alpha z times e to the minus j beta z, ax. Just recopy that. And then it's crossed. I'm going to circle that. That's a cross. And then I multiply by crossed into the H field conjugated. H field conjugated. So if I conjugate the A field, H field here, what happens? What does conjugation mean to you?
So
Inverse
what changes?
phase.
The angle here, right? And look, if I have e to the minus j quantity beta z plus theta, right? Take that whole quantity, and if I conjugate it, what happens is the angle becomes opposite in terms of its polarity. If it was plus 30 degrees, it'd become minus 30 degrees. So when I conjugate the H field here, I'm gonna get E naught, right? That's a scalar over the magnitude of eta. Then I'm gonna get still e to the minus alpha z, that's strict real. And then I'm going to get e to the j beta z, but I'm also gonna get e to the plus j theta n in the AY direction. Y'all see what I've done here? It's E times the E cross H conjugated. Now please look there for a second, make sure I get your attention when I do my next step. Are you with me? All right, now look. When I take a look at what this equals to, do you all realize the 1/2 comes out in front? 1/2. Now I know I'm going to take the real part of everything. Do you see how E appears here and E appears here, so it's E squared? E squared is going to be a scalar value, like 10, 20, 100. So I can take that out in front, but it's magnitude squared of E naught. Now, you see the magnitude here is just real too, right? Of eta. That can come out in front. Keep watching. What happens when I have e to the minus alpha z times e to the minus alpha z? E to the minus 2 alpha z, right? E to the minus 2 alpha z. Remember, power decays twice as fast as the E field or the H field, right? Because it's the product. Finally, I have e to the minus j beta z times e to the plus j beta z, which is, add the exponents, you get e to the 0 or 1, don't you, class? So that goes away. And the last thing I do, I have e to the j theta n, and I want the real part of that. Now, I do this a couple of times in the beginning of a course usually. E to the j of theta is really equal to cosine of theta plus j sine theta, isn't it, class? What's the rule? What is this called, this identity? Anyone?
Is that like a Pythagorean identity?
Something that goes in your car. It is Euler's identity, spelled EU, all right? It's very important you know Euler's identity. This is one form of it. The real part is only cosine. Another part is cosine of theta is equal to e to the j theta plus e to the minus j theta over 2. And you might as well write these down. Sine of theta is equal to e to the j theta minus e to the minus j theta over 2j. We use these three extensively in engineering. I'm surprised you haven't encountered in circuits or signals and systems, or both. Surely in signals and systems if you have me. Right? Now, that means the real part of this, the real part of e to the j theta n, is just the cosine of theta n, and the direction is x cross y is, class?
Z.
AZ. And this is one thing for sure. If you have a wave, a plane wave, the E field is perpendicular to the H field, but E cross H will always be the direction of propagation. And if you want a vector in the direction of propagation, find a unit vector in the direction of the electric field, cross it into a unit vector in the direction of orientation of the H field. That cross product will result in a unit vector in the direction of propagation. Everybody with me on that? It's that simple. So this right here is, in fact, the average power, P av of Z, which is S av of Z. So, and that has the units of, I might as well put that down here too, of watts per meter squared. And it's power flowing through an area. It's how much power is flowing. Not being dissipated by, but flowing through an area. Follow me, class? And that's it in a nutshell. Now, I'm going to leave that there. Continue on with my little investigation. So the next thing we're going to do is talk about, well, we're going to talk about one thing that's not going to be very hard to understand. This has to do with the type of polarization a wave has. Now let me explain something to you. If you have an electric field that can have, remember, if we have an electric field propagating that way, and it's oriented in the vertical direction, call it the x direction, propagating in z. If we took a snapshot in time and we could get on this thing, it would look like a vector this way, right? But as it propagates, what? The magnitude of this decreases, right? And then it even inverts, right? Goes this way. And then keep going a little further, it does this. But all the time, you can see that the electric field is either oriented upward or downward, right? So if you were to take a look at a position in space and you were just to watch the wave come through or come at you, you would see up this way or down this way. And if we trace the tip of that vector, it would make a straight line. That's called linear polarization. But the electric field doesn't have to be oriented this way. It can also be oriented this way and propagated, right? And then the electric field vector would trace a straight line this way. Does that make sense? Now, whenever the tip of the electric field at a given point in space traces out a straight line, that's called linear polarization. So this is linear polarization. And to make a long story short, usually what they do is assume it's propagating in the z direction. And then if it's propagating in the z direction, they call this x and they call this y. And they're going to assume it's coming out of the board like this. And for linear polarization, it will do something like this. The electric field tip will trace that pattern out. This is E tip right here. Does that make sense to everybody? So how do you describe that? Now there's probably innumerable ways of describing this, but in general what they do is say that Ex, or really E vector, will be equal to some E, call it E naught X times cosine of omega t minus beta z in the AX direction. So it's moving in the Z direction, but that's an AX component. Do you all see that there, class? This is time domain. Then it would have some plus some E naught Y, and it would have cosine of omega t minus beta z in the AY direction. Now if you take a look at that, just let z be 0 for a second. You see how the cosine omega t in both of those grows at the same rate, right? So an omega t is 0, it has a maximum value of 1, and EX 0 and EY 0 would be at a point. If you just do this, this is where you always find out kind of polarization. This is X and Y. If we look at t equals 0, z equals 0, t equals 0, we're going to get points here and here. Then if you make omega t equal to pi over 4, then both cosine of pi over 4, right? Cosine of pi over 4 is just 1 over the square root of 2, right? Then you're going to get another point here and here. But if you trace out all possible values of omega t, you'll just get this. And the slope of that line, no matter how you cut it, on the y direction, this would have a height E0y. And on the x direction, would have a maximum and minimum value of E0x. Do you agree with me, everyone? How many see this right here? This is a simple description without getting too complicated. That traces a straight line. Some people talk about the tilt angle as being important. I don't really care about that. That tilt angle is what? It's really just EY, or I should say for that one, it's going to be inverse tan of EX0 over EY0. But it's easy to get from trig, isn't it, class? Okay. So that's linear polarization. The next type of polarization, and the more general form, is called elliptical. Now, with elliptical polarization, if this is X and Y, you can almost gather what happens. You're going to have the tip of your vector trace out an ellipse. So it'll be something like this. That would be elliptical polarization. It means if we're at a given point, let it be z equals 0, and we looked at the tip of the vector, it would be tracing out this pattern. So how can we make elliptical polarization? Let me show you one way. There's a lot of ways to do this. One way is we can say that here, since we're at z equals 0, I can say that the electric field is going to be given by some E0. I'm just going to call this a single value here. And it's going to be cosine of omega t minus beta z in the AX direction. And then it's going to be plus E0 times cosine of omega t minus beta z, but plus a phase angle. And I can make it anything. I can make this phase angle pi over 4, for instance. That would be 45 degrees. Now I want you to see what happens when I do this. Remember, that's the general form for, and this is AY, by the way. That's a general form for an electric field propagating in the z direction that has both x and y components. But now there's an angle, right? So let's see what goes on here. Work with me here. I'm going to go ahead and do a little plot in my mind, in your mind too. Call this x, call this y. Let's allow z to be equal to 0. That means I get rid of it, which makes things easier. So now I have this, don't I? If z0, it goes away. Now when I look at that, start plotting points. First point we're going to do is omega t equals 0. Well, when omega t equals 0, this is 1, isn't it? And this is going to be the cosine of pi over 4, 1 over square root of 2, isn't it? Cosine of 45 degrees is 1 over square root of 2. So what do I do? As a matter of fact, let's normalize this. Let's divide it by E naught to make my life easy. We can multiply by E naught later. So when omega t is 0, now the value in the x direction is 1. Call that 1. Call that 1/2. But the value in 1/2. The value in the y direction is what? Class? When omega t is 0, the value in the y direction is cosine of pi over 4 or 0.707, right? So it's about here, right? So that means my first point would be about here. Call that point 1. Right? Just work with me. Now, when omega t is pi over 4, right? Now what happens to the x direction? Cosine pi over 4 is 1 over square root of 2 or 0.7, right? So this is about here, right? And we're about in the y direction, what is it? Cosine of what? Pi over 4 plus pi over 4, or cosine of pi over 2 is? Cosine of 90 is? 0, exactly. So that means the y component is 0. So I went from here to here. You all see the direction this is going, right? Now keep going on. What about omega t is equal to pi over 2? First one is what? What is cosine of pi over 2? 0. So I know as far as the x direct, I'm going to be right here in x, right? Where am I on y? Cosine of what? 3/4 pi, right? What is that? Here, look, you know how cosine wave looks? Just imagine this. Cosine wave starts at 0, at pi over 2, it goes through 0. I mean, starts at 1, goes through 0 at pi over 2, right? And then it starts going negative, right? So at 3/4 pi, it's a minus 0.707. Do you follow? So that's a minus value. So now it's down here. So now I'm here. And that's the third point. Here's the second point. And you can see what's happening here. I'm forming an ellipse like this. You all see that? Now, this is the simplest way to plot these. You just increment in about 45 degrees fashion. You see which way the tip's moving. It starts here. This isn't a good drawing, but this would be a perfect ellipse around there. It starts here and it's moving this way. And here's my next point. And I want you to listen to this very carefully because we're going to dictate something called the type of polarization. beyond just linear, elliptical, or circular. Now, if you take a look at this, and you take your right hand again, assuming you have one, and the first thing you do is you put your thumb in the direction, on your right hand, of the electric field. I mean, of the propagation. So it's propagating the plus z, right? So it's x cross what is y, z would be out of the board. You follow me on that? Now, if you go ahead and take your finger, your index finger on your right hand, and put it there, and if the sense of rotation of that tip is in this direction or counterclockwise direction, it's considered right hand circular polarization, right? But if you have to take your left hand and put it in the direction of propagation, and your index finger's in the direction of the tip of that vector, and it's winding in the proper way, or towards your like closing a door, then that's left hand polarization. Now this is elliptical. Which way is it going? Isn't it left hand polarization? How many see it's left hand elliptical polarization? So you would label this way left hand elliptical polarization, or LE or LHEP. I'll tell you why it's important in a second. All right, now that's what a plus pi over 4. What do you think happens if I make this minus pi over 4? Just take a guess. Well, if it was rotating this way before, which way do you think it's rotating? The right-hand circular polarization. Not only that, the ellipse will do this. I'm not going to prove that, but it will now look like that. So the sine of that angle, really it's the angular difference, but what I always tell people is just plot 3 or 4 points. It's the easiest way to see which way the tip's moving. You've got the direction of propagation. If you have to use your right hand and then do the old door closing on it like that, and your index finger tracks the tip as you close the door, I should say open the door, then it's right hand. If it's not doing that, it's left hand. That's as simple as it gets. All right, now there's one case that's probably used more than any when you talk about polarization. It's when it makes a perfect circle. That's elliptical, and that's circular polarization. Circular polarization is this. This is X, and this is Y, and this is your electric field. It never changes in magnitude. It has the same magnitude for all time. The only thing that changes is the orientation. But it's propagating in the Z direction. So the way you could describe that, if you wanted circular polarization, is this. You can come in right here, and you can simply add or subtract pi over 2. And that will give, and then make this just E naught, and make that E naught. And that will give you this, where the extent here would be E naught, and the extent here would be E naught. And what it is just going to be a hand that's moving either that way or this way. And that's called either left hand or right hand circular polarization, or left hand circular polarization. Now, one thing about this wave that's unique that I want to mention. A circularly polarized wave, I saw the E field never changed its magnitude. You see that? That means the instantaneous power is always constant. In other words, there is no peak, trough, like it would be in linear. It's a continuous amount of power, and there is no variation in time. It's a continuous amount of power in this waveform. There's something else I'm going to tell you about this. This is a little further down the line. This is very important to radar, and it's important in general, but to me personally, because I do radar work, it's very important. When you send out a right-hand circularly polarized wave, and it strikes something that's a conductor, it reflects back a left-hand circularly polarized wave. Now, why is that important? Because if I send out a circularly polarized wave with a certain frequency, and I know it's right hand, I know when it hits things, it's going to reflect back at the same frequency, but it will reflect back a left hand. And I can design a filter that will filter out anything but left-hand circularly polarized waves at about that frequency. And then I can get rid of a whole lot of interference, and that's the advantage of circular polarization. Doppler weather radars you've heard of, they use this. They can distinguish heavy rain from graupel. Graupel is like slush, to hail. They have an amazing amount of information they get when they use circular, sometimes elliptical polarization for different reasons. You understand, everyone, class? And that's real important to understand why circular polarization or maybe elliptical is so valuable, because now you can distinguish what is reflected back to you. That's very important. And I could spend a little more time on this, but it'll be later in the chapter, or later in the book, actually. And I don't spend a lot of time with polarization because, honestly, there are so many ways to mathematically describe this phenomenon. It's almost, we could do it with science. You all agree we could do it with science? We could do it just in terms of phasors. We can do it in a lot of ways. It doesn't merit the time. I mean, there's no reason to spend time on a mathematical description where that's as good as you need. Okay. Now, plane wave propagation in general, and then reflection off surfaces. That's where I wanted to get today. You know, you had transmission line theory, and you realized with transmission line theory, usually your load that you terminate into, it determines how much is reflected, right? And how much is actually absorbed by the load. That's the same thing with when we're doing what we're about to do with electromagnetic waves that are going to be striking a surface. And this is important, so let me watch this. Okay. So now we're talking about, we're going to be talking about waves and reflection, or waves and reflection. And the first thing we're going to talk about is normal incidence. And let me set you up primed for this one. So let's say we have two different regions. Region 1 we'll call air, and that has a characteristic impedance of eta naught. And eta naught is simply equal to 120 pi ohms, or 377 ohms. It's free space. With me? Now I'm going to say, I better draw some coordinates here. Call that the z-axis right here. Why don't we call this the x-axis in this direction? And now we're going to have an electric field. And the electric field, we're going to say, is oriented in the x direction, and it's propagating in the z direction. That's that little squiggly line there, means propagation. And we're going to say that this electric field in region 1 here, the E field in region 1 is dictated by E. Matter of fact, why don't we make this region 0? It's going to be E naught times E to the minus, I'm going to go to beta. We're going to assume this is lossless. We can extend it to lossy. So this is going to be a lossless case. E to the minus J beta in region 0 times Z in the AX direction. Now y'all follow me right there that what I've got is an electric field that's propagating in the Z direction, but it's what? Oriented in the X, correct? How do I get the H field here, class? That's the E field. H would be what? Remember how? We can get this real easy. Well, I know formally it's what? It's 1 over the eta of the region, which is eta naught, times the unit vector in the direction of propagation, which is AZ, right? And it's crossed into the E field, which would be E naught, E to the minus J, beta, 0Z, AX. Do you all agree with me? That's simply 1 over eta, a vector in the unit vector in the direction of propagation crossed into the electric field vector. Correct, class? by definition. Well, what's that gonna be? That means the H field here would be equal to E naught, right? Over eta naught. And what happens, it's still times e to the minus j beta z, right? Beta naught z. And it's times az time crossed into ax, which is ay. Now something I'm gonna tell you, you don't do that over and over again. If I know what the electric field is, and I know it's when I say normally incidence, the way I like to think of normal, if I'm looking right down at the floor and I take an arrow and fire it into it, it's banging straight out of the surface, that's normal incidence. It means the wave whacks it normally, comes straight in, down on it, right? Anything other than that is oblique. It's coming in at an angle. So this is fine. When you have a normally incident wave and you want the H field, you just take the E field and divide it by the characteristic impedance. That'll give you the H field's magnitude. And you find the direction, knowing that the E field crossed into the H field is going to be a vector direction into the way it's propagated. So I can just, by looking at that, say if I have AX and it's going in AZ, it has to be AY in terms of its orientation. So that's the H field, right? That's the H field right here. Now, there's something else that happens though. That's region 0. I'll call this region 1 here, right? We're going to have another electric field that happens. That's the one going that way, but these are all, this is an electric field in the plus Z direction, right? But when the wave hits this, we're going to get a reflected field, aren't we? So here we're going to get a reflected E field, E reflected, and the E reflected, I'll just put that over here, the reflected field will be equal to some E naught reflected times E. Now this is going to be going in the plus J beta Z region. It's not going in the positive, but the negative Z direction. Follow me? And the E field will still have the same AX orientation, but now it's moving the opposite direction. Are you with me, class? Now I'm going to do it this way. Do you all agree that I could get H by saying 1 over eta, right? Then the direction of propagation crossed into the E field. We'll do it that way one time. So I can say now my H field in the reflected way would be equal to 1 over eta naught. What's the unit vector in the direction of propagation? Minus AZ, very important. So now it's minus AZ, right? Times e to the j beta z, and it's times the reflected field, which is going to be E naught reflected, times e to the plus j beta, and this is really beta 0 z. I don't know if I put beta 0, yeah, I put beta 0 there. Beta 0 z times AX. Now what do you see the reflected field becoming? It's going to be E naught reflected, right, over eta naught. And then it's going to be,
There's supposed to be
sorry,
across.
I got 2 of them in there. Should be 1, pardon me. And it's going to be times e to the j beta naught z, right? And then we have z cross x is, az cross ax is it?
Yes.
Ay, but with a minus sign, it's minus ay. Correct, class? Yes, sir.
Is that an exponent for the E naught at R?
This, you mean?
No.
No, it just says reflected. E0 means it's a scalar value that's not going to change. The R means it's reflected. And here, I should have said incident right here. I'm sorry I didn't. This should be an incident, but there's either reflected or incident. Do y'all agree with this? Now something else that happens, you also have a transmitted wave. You're going to have a wave here that transmits. And it will be, the E field will be in the X direction, so you're going to have some EX transmitted, or EX, call it not EX, call it E transmitted, and that's going to be some E not transmitted, E to the minus J, and here it's beta 1, because that's region 1 times Z, and it would be in the AX direction. Now, it's the same as the incident field, except for one fact. now it's got a different value of beta. Here, in this region, the value of beta, right, would be equal to really omega times square root of mu naught epsilon naught, or omega over c if it's the speed of light. Here beta would be equal to omega times square root of mu 1 epsilon 1. And that would be beta 1. The values will be different. When you do some of the problems, you appreciate this. And remember, there's also, this is eta naught, there would be an eta 1 here, and the eta 1, since it's lossless, would be the square root of mu over epsilon for that region. Not mu naught over epsilon naught. That's important to realize. So that's the transmitted electric field. What would the transmitted H field be? You know, I don't know if this current. Do you see the incident H field is just EI over eta naught in magnitude? Well, the transmitted H field is going to be E transmitted divided by eta 1. It'll still have e to the minus j, not beta 0, but beta 1 times z. It'll still be in the AY direction. So this is going to look just like that, except now it's E naught transmitted over eta 1, not eta 0. And it's e to the minus j beta 1z in the AX direction, or I'm sorry, AY direction, pardon me. AY direction. Okay? Are you with me? Now here's where it becomes important you see this. The way we figure out what we call the reflection coefficient or transmission coefficient is we equate the values of the electric field at the boundary. You've heard this in EMAG 1. Do you remember E tan 1? The tangent field in region 1 was equal to the tangent field in region 2. Do y'all remember that? Now what is tangent? Well, if I'm talking tangent to this floor, it would be something in the plane of the floor. Like if an electric field had this orientation, anywhere in the horizontal direction, it would be tangent. Normal would be perpendicular, this way. All right? So when we talk about E tan 1 is E tan 2, what we do is we look at the point z equals 0 and we equate them. And it's smart to always put the separation between two regions at z equals 0. Follow me that, class? So when I look at this, well, this is the description of the electric field in region 1. The incident field is E0 incident times e to the minus j beta z. If z is 0, it's just E0 incident, right? It's in the x direction. But there's also a reflected field. It's going to be E reflected, right? So I can say that E naught incident plus E naught reflected equals E naught transmitted. And that's at the boundary. On one side of the surface of the boundary, it's just E transmitted. On the other, it's the reflected plus the incident. With me, class? You all see this? So that's one equation, and box that. Now the second equation is H tan 1 is equal to H tan 2. Do you remember that from EMAG 1? H tan 1 is H tan 2. Now that's assuming there's no surface current. There is none here. There's no force current. So when we do that, well, what's your tangent field in region 1? Take a look at it. In region 1, we have this, right? E naught incident over eta naught, right? It's equal 0. And we have this right here, which is minus E naught reflected. So we're going to have E naught incident over eta 0 minus E naught reflected over eta 0 is equal to E naught transmitted over eta 0. And you don't have to put the AYs there. Did y'all see that, class? That's the H field on one side is equal to the H field on the other side. You'll notice that negative sign. Now, what we'd like to do is get something called the reflection coefficient. And the symbol for that is gamma. You're used to seeing that. There's usually a subscript that talks about the boundary, but don't worry about that. This is the symbol for reflection coefficient, it's capital gamma. So the reflection coefficient is generally given as the value of the reflected field's weight divided by the incident field's weight. And that's exactly what it was for transmission lines. Remember, the reflection coefficient was a ratio of the voltage reflected to the incident voltage. So if we're going to do this, well, I could say I could take this equation, this is A to 1 here. Let me do it this way. I can take this equation, you don't have to write all this down, you can just watch and see. I'm going to multiply both sides of this equation by A to 1, A to naught. So when I do that, I get this, and I get this A to naught. You all see what I've done there? I'm simplifying. Now what I'm going to do is get a value. What I want is just E naught T, or I want the value of the transmitted field, so I divide S by A to naught. Right? Are you with me? And I set it equal to this. So that's equal to just E naught incident plus E naught reflected. Are you with me? Now I divide both sides by E naught incident. This is the easy way to do it. When I divide by E naught incident, what do I get? Now I have A to 1 over A to naught. I have E naught incident over E naught incident is 1 minus E naught reflected over E naught incident. That's the reflection coefficient. That's equal to E naught incident over E naught incident 1 plus the reflection coefficient. With me? And now I can manipulate this. I can go ahead and I can say, manipulate it right here. I can say that A to 1 over A to naught, right there, minus 1 is equal to the reflection coefficient times 1 plus A to 1 over A to naught. And then I multiply both sides by A to naught. When I do that, I get this. And then I divide both sides by A to naught plus A to 1, and I get the reflection coefficient given as A to 1 minus A to naught over A to 1 plus A to naught. And that is the reflection coefficient. The easy way to think about this, it's just like the reflection coefficient for transmission lines. It's always the impedance you're going into minus the impedance you came from over the sum of the two. You all follow me in that class? So let me ask you this. What's the reflection coefficient when eta naught equals A to 1? Just look.
0.
It's 0. It means it's matched, right? There's no difference in the median. What happens, what's the reflection coefficient when A to 1 is 0? Now look at it. If A to 1 is 0, what is it?
Negative.
Minus 1, right? What is the reflection coefficient when A to 1 goes to infinity? One plus 1. Look, if it goes to infinity, it's really this divided by A to 1 by A to 1 is 1, right? And those are like open circuit, short circuit, match circuit. Back in the day when you did T-lines. Remember? You had an open circuit, the reflection coefficient is 1. A short circuit, the reflection coefficient was minus 1. And a match circuit, the reflection coefficient was 0, right? So those are the three cases. And they're pretty obvious. And that's really, that's it in a nutshell. I'm going to make one comment too about this with power flow. So if we have power flow, let me redraw that region. So this is region 0, and this is region 1, right? I had eta naught here, I had eta 1 here, I had beta naught here, I had beta 1 here. Now, I assume I have an incident field in this direction, and I have a reflected field going in this direction, and I have a transmitted field going in this direction. And I want the power, right? I want you to listen to me. First, this is a lossless region. I'm assuming it's lossless. Power flow in a lossless region, please write this down. This is going to be power flow in a lossless region this is actually power density. That's 1/2 the real part of E cross H conjugated, right? Now just listen to me. Y'all realize that H is equal to the E field divided by eta, right? And there is no alpha. Let me do this for you. I'm going to do this power flow just for the positive traveling positive traveling field in region 0. So, you know the E field incident was some E naught incident times e to the minus j beta 0 z ax, and the H field incident was equal to E naught I over really eta naught, it's strict real, e to the minus j beta naught z ay, right? Now keep watching. When I evaluate this for that region, I'll do it here. I take P av of z is equal to 1/2 the real part of E crossed into H conjugate. What is H conjugate going to be? Still going to be E naught over eta, right? Eta naught, that's strict real. But what happens when I conjugate that?
Plus JB.
Exactly. And it would be AY. And what happens? Y'all see this e to the j beta business cancels. You get 1 times the other is e to the 0 is 1. And I really get, and this is important you see this, 1/2 magnitude of E naught incident squared divided by eta naught in the AZ direction. And in general, whenever you're talking about power flow in a lossless region, or approximately lossless, if you have the electric field, that's the only thing you need. If you have the direction of propagation, it assumes the direction of propagation. You take that electric field, square the value, divide it by eta naught, and multiply it by 1/2. That gives you the power in watts per meter squared. The AZ is the direction of propagation. Are you with me? Now, if you think about power flow in this problem, I hope you can see this. Well, I have power flowing this way. I'll call it P av positive right here, and that would be 1/2 magnitude of E naught incident squared over eta naught in the AZ direction. That's going this way. You all see that, class? But there's power flowing in this direction. That would be P av in the minus direction. It's still going to be 1/2 the magnitude of the reflected field. But what's the magnitude of the reflected field? Well, it's the reflection coefficient, right? Times E naught incident squared divided by A naught, but this is in the minus AZ direction. You follow me? Now we've got transmitted power too. And P av transmitted will be equal to 1/2 magnitude of the transmitted field. This I didn't talk about yet. I got the reflection coefficient. I want you to see something. I can manipulate these two equations, this equation and this equation, and I can get a transmission equation, transmission coefficient, all right? And here's the interesting thing. Please write this down in the corner here. The transmission coefficient The symbol for that is tau. And tau is nothing more than 1 plus the reflection coefficient for plane waves. Now, if you think about this, tau is equal to 1 plus the reflection coefficient. Well, that's eta 1 minus eta 0 over eta 1 plus eta 0. Isn't it, class? Now, if I go ahead and take 1 and put eta 1 plus eta naught over eta 1 plus eta naught, and I do this, I'll end up with, it's really twice eta 1 over eta 1 plus eta naught. That's the transmission coefficient. It's just twice times the impedance you're going into over the impedance you came from plus the impedance you're going into. Okay? Now, here's something interesting. I got the average power flow. I hope you can see this. Average power flow going that way, average power flow coming this way, correct? Reflected power flow. The total power flow would be this minus this. Do you agree with me? All right. How much power is flowing here? It would be 1/2 the magnitude of the transmission coefficient times the incident field squared over eta in region 1. And this is something I didn't say, but I should have, but the transmission coefficient is the ratio of the transmitted electric field over the incident electric field. Are you with me? Now take a look at this, and it's important you see this. When I take a look at the total amount of power going in this direction in region 1, it would be, this is P total, it would be in the AZ direction. It would have a 1/2 magnitude of E naught, right? The E naught incident squared. And then it would have 1 going that way, but you would subtract and make sure you put the magnitude of gamma squared going this way. It would be in the AZ direction. That's the total amount of power moving in the plus Z direction. Do you all see that, class? With me? Well, that has to be equal to the total amount of power that is transmitted. And this, in fact, is equal to PAV. It's equal to 1/2. When I put that, that's right here. It's equal to 1/2 times E naught incident squared over eta 1 times tau squared. Magnitude of tau squared. Now please watch this next part. It's important. And this only is good for normal incidents. Are you with me so far with what I've done? So now if you take this, just look for a second here. And this would be in the AZ direction as well. Y'all see I can get rid of AZ. Agreed, class? Both sides. I can get rid of the 1/2, can't I? Can't I get rid of E naught too? Now, I shouldn't have done this, but this had a 1 over eta naught on it, didn't it? Right? And this has a 1 over eta 1, but I should get rid of E naught here. So now you can say this for power transfer. You can say 1 minus the magnitude of the reflection coefficient squared divided by eta naught, pardon me, is equal to this squared transmission coefficient over eta 1. And this is true because it's for power transmission. In fact, it's normally incident power transmission. Are you with me, class? And that's important. Now, next thing, I gotta do oblique incidents, but I almost feel at this point it's worth doing a problem or two just to capture some of this stuff. So let's do it this way. Here's a typical problem you might see on Friday. Very typical. We sort of went ahead and we calculated intrinsic impedance, we calculated power, we calculated propagation factor, we calculated everything in lossy media and in non-lossy, and now we've taken a look at the reflected and transmitted fields where there's a barrier, something that has a different set of properties. So now, probably good to just do a simple one like this. Whitmer's book has a lot, but I'm going to just make up one. Work with me on this and get your calculators out. And always try to bring your calculators to class and always your book. Now, he's got a problem. I see you got your book open there. Let's say I have a region, and in the first region, I have eta naught, well, I'm going to have, say, just mu naught, epsilon naught, which means eta naught, and we're going to assume this is going to be a frequency of 100 megahertz. All right. Now, the second region, there's first region. Second region is going to have epsilon equal to 2 epsilon naught. And that's good enough. And what I want you to do is tell me if I have, say, a electric field here in the x direction, call this z, call this x. Electric field in the x direction equal to 100 volts per meter, propagating normally incident into this. And I want to know both the electric field transmitted, and I want to know the actual power density, PAV, that's transmitted, the average power transmitted. So, let's do it. First of all, what do I need to do this problem? Here, assume this is mu naught, and it's lossless. Guys, what do we need? Well, don't I need the transmission coefficient or the reflection coefficient? All right, so how do I get those? What do I need to calculate those, say? I need the intrinsic impedances, don't I? So let's think about this. Since, isn't this air, epsilon naught and mu naught there, right? So you know the intrinsic impedance for that case would just be the square root of mu naught over epsilon naught, which is 120 pi ohms, right? 120 pi ohms. Now over here, I need that too. And so over here, eta in region 1 in this case would be equal to the square root of mu naught over 2 epsilon naught. What's that going to be? Just look. If mu naught over epsilon naught was 120 pi, what's mu naught over 2 epsilon naught? 1 over the square root of 2 times epsilon naught, isn't it, class? Or simply 120 pi divided by square root of 2 if I want to do it that way, ohms. Correct, class? Now, since I'm actually looking for the transmitted power, I could use the transmission coefficient, couldn't I, guys? What's the transmission coefficient? Well, it's 1 plus the reflection coefficient, if that helps. And it's also 2 times eta 2 over eta 2 plus eta 1. It's always twice the impedance you're going into over the impedance you came from plus the impedance you're going into. What's that going to be? That's going to be 2, right, times eta naught over the square, divided by 1 over the square root of 2, divided by eta naught plus eta naught over the square root of 2. Now I'm taking the liberty of just using eta naught there so you see it cancels. You see, everybody, it's twice the characteristic impedance you're going into. The characteristic on impedance I'm going into is eta naught over the square root of 2, isn't it? 125 over the square root of 2. Right? Where did I come from? Eta naught. Where am I going? Eta naught over square root of 2. Now you'll notice the eta naughts cancel. So now I have what? I have 2 times this 1 over square root of 2, or really square root of 2 up top, over 1 plus what? 1 over the square root of 2 here, correct? You agree with me? What's this going to be? Can you give me a calculation? What is it?
0.83.
That sounds about right. Anybody else second that? Don't get tired like me. Are you with me though? I have that. Now I wanted the electric field transmitted, it's magnitude only. I don't care about magnitude usually. So the magnitude would be what? The incident electric field 100 times what? Come on. Transmission coefficient, right? Right? We just calculated. 4 times 0.83, or it would be 83 volts per meter would be the electric field transmitted. Do you all agree with me, class? Right? All right, what's the power density transmitted? Now the average power transmitted. This is watts per meter squared. What do I need? It's lossless. What did I say this is going to be? 1/2, right? Magnitude of the transmitted electric field, right? Which is 83 squared divided by eta in that region. Eta in that region is what? 120 pi divided by square root of 2, correct? So what's this value going to be? And that's in watts per meter squared. Anyone? Anybody get it? $83 squared divided by 1/2.
Almost 13 here.
12.9 watts per meter squared. And that's how you do a problem like that, using really the intrinsic parameters to get the transmitted reflected power. Remember this for Friday, that there's closed book, closed notes. All right? I'm going to let you have a calculator for this one. It's closed book, closed notes, no wearable electronics, no use of phones, or make you take your phones out and dump them over. I've caught kids cheating with these either Apple or Google watches, and they had a little scrolling thing one time. And, you know, I mean, you're always going to get people, desperate people do desperate things, and I hate to see a kid, you know, ruin his career doing something stupid like that. So please don't. Be honest. And let's see, it's 27. Is there any questions at all? I mean, I don't have any clue if you've been doing the homework or not. I gave you a bunch of them. They're not tough, but you should be keeping up with them, because this stuff's going to start piling up pretty fast when we hit oblique incidents. I don't have enough time to really do it justice to oblique incidents, but that's when all of a sudden the electric field is not coming in normal. And it's coming in at an angle, and it could be either TE or TM polarization, and the transmission reflection coefficient get hairy, and you get something called a Brewster's angle. You studied in physics, if you remember that. And you also get the critical angle. Does anybody remember what the critical angle was? Does anybody remember Snell's law? You ever hear that before? What was Snell's law about? Physics. It was in optics. Anybody? It said how light or electromagnetic energy bent through another medium, from one medium to another. And you remember, anybody here shoot, or anybody here an archer? Ever shoot a bow and arrow? Well, anybody ever shoot at a fish in the water? What do you have to do? Aim way under, right? Because light, if this is the surface of water, the light beam diffracts towards the normal, almost straight down. And if you think about that, means you go like this. So if a fish is here, it would appear to be here. it would appear to be much, much higher. You have to shoot way down. Now, I was bowhunting one time with deer, and deer saw me, and I was on the ground, I fired an arrow with a recurve, and the thing just stepped out of the way. That's just the last time. Last time. Nothing's gonna step out of the way of 30-06 bullet, so, or 270, so. I became fervent believer in rifles for animals. If you're gonna hunt them, eat them.
How many questions have